Let's get a better understanding of the fundamental theorem of calculus part 1 by looking at functions that are written in terms of an integral. Remember, in the fundamental theorem of calculus part 1, we know that our accumulation function is a function of x, and that variable x must be at the top of the elongated s before we could actually apply the derivative. So for this first example, we're going to change the way r of x looks. We're going to use properties of integrals. So we're going to have an opposite sign, and our domain changes from 2 to x. And now we have the variable x at the top of the elongated s. Now I'm ready to take a derivative. I'm going to go ahead and use Leibniz notation. I find it to be much easier. And we're going to go ahead and simplify this expression. Notice we just have a constant of -1. And so we have a constant times a function. We have a constant of -1 times a function of x. What can we do with that -1? We simply put it out in front. And this expression will have the same value as the next expression. And the next expression is simply this function of x. By the transitive property of equality, we could conclude that the derivative of r with respect to x is equal to this function of x. Example 4. We're going to do a similar procedure, but we do need to be more careful. First thing we're going to do is rewrite k of x so that we could see our variable x at the top of the elongated s. Notice we don't just have an x variable, we actually have a sign of x. This is actually an observation of a composition of functions. So we have to be a little bit more careful here. We're ready to take the derivative. Let's take the derivative of k with respect to x. Once again, we have a constant. And so the derivative of a constant times a function of x, we could put that constant out in front. The constant of -1 goes all the way to the front. And now we have to analyze this function. I'm going to change this slightly. And we're going to do a u sub here. So off to the side, I'm going to do a u sub. I do need a different letter. Why don't we call it h of x? And h of x is actually a composition of functions. So remember from the chain rule, the derivative of h with respect to x will actually equal to the derivative of h with respect to u times the derivative of u with respect to x. Now, what is h of u? H of u is this u substitution. So derivative of h with respect to u is simply going to be 1 plus u squared. Now, what is u of x? U of x is our inside function, also known as sine of x. So when you take the derivative of u with respect to x, you just get cosine of x. And we're ready to substitute. This expression is going to have the same value as the next expression, which is -1 times the derivative of h with respect to u times the derivative of h with respect to u, which is simply the square root of 1 plus u squared. But what is u? U is actually sine of x times the derivative of u with respect to x, which is cosine of x. So this is a great application of the chain rule. Reinforces your understanding of functions. We need to write a conclusion sentence. By the transitive property of equality, we now know the derivative here. The derivative of k with respect to x is equal to this function of x. Let's look at one more example to get a better understanding of this fundamental theorem of calculus part 1. We have a function here, but it is very hard to depict. The interval is going from x to x squared. Remember, in the fundamental theorem of calculus, we would like g of x, or some function of x, maybe we'll call it m of x, needs to have a finite number at the bottom of the elongated s. We need a variable x at the top of the elongated s. And then we have a function, a continuous function, with a dummy variable t. And m here is going to be an antiderivative of lowercase f. For this particular example, we're going to have to split this interval. Now, the interval is going from x to x squared. We're going to split it with some real number a. So if you have an interval here, x to x squared, we're just going to put an a value there and split it. First thing we're going to do, take this interval x to x squared, and we'll split it with some a value in between. What does that do to g of x? It allows you to use properties of integrals. And we're going to pace the other interval from a to x squared. And we get something like that. This is still a function of x. We're going to rewrite g of x again using the properties of integrals, properties of definite integrals. And notice we are getting very, very close to getting the fundamental theorem of calculus, part 1. We are ready to take a derivative. This is simply the opposite of this function of x. And the next one requires some very, very careful manipulation of the chain rule. We need the derivative of the outside function evaluated at the inside function. There it is, times the derivative of the inside function. There it is. Therefore, we have the derivative of g with respect to x. It is simply going to be this function here.